Welcome back, everybody. This is our fourth session in JEE mains previous year questions for chapter Alternating Current of class 12th. Before this video, we have made 3 videos in this series, and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET previous year questions. And if some of friend you are preparing for NEET, or if you want some additional practice, then you can watch those videos also. If you find these videos helpful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. In the previous one, we completed up to around question 20. This was the last question which we completed, and today we will start with question number 21. So in LC circuit of inductance L is equal to 40 millihenry and capacitance 100 microfarad. Voltage is given to us, is applied to the circuit. The current in the circuit is given by. So here we have we can say inductor and capacitor, both are in the circuit, means both will provide their own impedance, and depending upon the value of impedance we will get the value of we can say current, that how current varies. Either it will stay in front of potential, or stay ahead of potential, or stay behind of the potential. So let's start. So here we have XL, that is the impedance offered by the inductor. Let me slightly make it thinner. XL will be equal to omega times L, and that will be, omega is 314 here. So 314 multiply L, that is 40 into 10 raised to power minus 3. And solving this, we will get 12.56 ohm. Similarly, XC will be equal to 1 by omega C, and that omega is 314 multiply C, that is 100 microfarad, so 100 10 raised to power minus 6, and this will result in 10 raised to power 4 by 314 and equal to 31.85 ohm. So total impedance of the circuit will be equal to R square into R square plus XC minus XL square. Now in the statement, question statement, no value or nothing is mentioned regarding the resistance. So we assume that this circuit does not have any resistance. So R is 0. So 0 square plus 31.85 minus 12.6 square, that will be 19.3. So 19.3 whole square, or Z comes out to be 19.3 ohm here. So now from this value we can calculate value of current, that will be peak value. As here this is the peak value, so this will be the peak value of the current. Peak value will be peak value of the potential divided by the Z. So 10 divided by 19.3, and that will give us 0.52. Now let's find out the value of the phase, that what will be the value of phase, or phase difference what will be. So phase difference tangent phi will be given by XC minus XL divided by R. Now XC minus XL is already we know, that is 19.3, and R is not known to us, so we assume that value of R is equal to 0. So it is 0, or we can say tangent phi is undefined or infinite. From that, phi is 90 degree, and this is a capacitor dominated circuit. This is a capacitor dominated circuit, means current will lead the voltage, or this phi will be positive, or we can say I will be I node, that is the value of I node, I peak which we calculated, into we have sine of 314t plus 90 degree. This is the leading of the current as respect to the potential. So the whole value will become 0.52 sine 90 plus theta is cos theta. So it will be 0.52 cos of 314t. So here it is. Option A will be the right answer. Let's move to the next one. As shown in the figure, the battery of EMF E is connected to an inductor L resistance R in series. The switch is closed at t is equal to 0. So switch is closed. The total charge that flow from the battery between t is equal to 0 to t is equal to Tc, where Tc is the time constant of the circuit. So here we have to find out total charge flowing, and total charge flowing can be calculated using the we can say equation of the uh, current flowing through the inductor. We know that current through inductor follows this equation, I node into 1 minus e minus t by tau, where tau is time constant and it is given by L by R. We know that I is equal to I is current, so it is rate of flow of charge, so it will be dq by dt. So dq by dt is equal to I node 1 minus et tau. From this, dq comes out to be I node 1 minus e minus t tau into dt. Now let's find out the value of I node. So I node is maximum current in the circuit, and that maximum current is equal to when inductor is fully charged, so it is offering no impedance or no cross voltage. So in that scenario, I node will be equal to E by R. So let's move ahead. So dq is equal to E by R 1 minus t tau dt, and as we have to find out total charge from 0 to Tc, where Tc is time constant, means tau. So 0 to tau we will integrate the whole equation. Now this will be the charge up to time tau. This will be E by R as it is. Now integrating this 1 into dt, integration will be t, minus integration of this will be e raised to power minus t by tau divided by minus 1 by tau, with limits of tau to 0. Further, this will become e by r t minus minus plus, and tau will come up. So this will be tau times e raised to power minus t by tau, with limits of tau to 0. Now value of tau is already known to us, that is time constant, and for LR circuit it is L by R. So when we substitute the values of the limits, we will get E by R. Here putting substitution value upper and lower limit, we will get tau minus 0, or L by R minus 0, or in short L by R, plus tau times means L by R times e raised to power minus. Now for this t we have to put tau, so tau by tau will be 1, so it is minus 1, so e raised to power minus 1. And when we substitute t is equal to 0, this whole term will reduce to 0, so minus 0. So that's we have. Now e by r, we can take L by r common, Oh, sorry. Wait a minute. We made a mistake. When we put t is equal to 0, so we have tau here already. We already have tau here. Means this will be tau. Let me rewrite this. When we put t is equal to tau, so it will be tau times e raised to power minus 1, or tau is L by r e raised to power minus 1. Negative, when we put t is equal to 0, so it will be tau times e raised to power 0. E raised to power 0 is 1, so we will have only tau, that is L by r. So this L by r is cancelled from each other, and we will have e r into L by R, and e raised to power minus 1 is 1 by e. So it will be EL by R square into E. And if we match the options, we can see that none of the options matches here. I think there might be some mistake because we have already solved similar type of question, and I think there is E is missing in this option. If E is there, then this option will be the right answer. Now let's move to the next one. A LCR circuit behaves like a damped harmonic oscillator. Comparing it with a physical mass string damped oscillator having damping constant B, the correct equivalence we have to find out. So either you can just remember the value that inductor is, we can say, let me write it, that L is analogous of mass, R is resistance, and resistance is related to damping. So resistance is analogous of damping constant, and our spring constant is Q by C analogous. So these are the analogous value, and we will also solve them. So for a damped harmonic oscillator, we have equation that F is equal to minus Kx minus Bv, and we can write it like F is equal plus Kx plus Bv is equal to 0. Now force can be written as mass times second derivative of distance, velocity, acceleration, plus velocity can be written as dx by dt and k times x. So it is a differential equation, second order differential equation in x. And we will form similar equation for the LCR circuit. Now suppose now we have a LCR circuit. So this is our inductor. Now we have capacitor, and now we have a resistance here, and it is connected to a battery. Battery is ideal of EMF E. This is inductor L, capacitor C, and resistance R. Now what will happen that as we turn on this circuit, this inductor will charge, capacitor will charge, and after some time that current stop flowing in the circuit. And now we remove the battery from the circuit and connect them to each other. So short circuit the circuit. So now we only have LCR, and inductor is also charged, capacitor is also charged, and initially there was no current. And as we connect this circuit or short this circuit, there is some charge flowing in the circuit. So some current flowing in the circuit. So suppose I current is flowing in the circuit. So this is the direction of the current I. Now this side will be positive for inductor as current is flowing from we can say left to right. So left, if current is entering from the left, so it will be positive, leaving from the right, so it will be negative. Similarly for capacitor, this will be positive, negative, and similarly for the resistance, this will be positive, negative. Now let us write an equation, Kirchhoff's equation for this circuit. So we will have potential across inductor is L di by dt, and positive to negative we will get negative, so minus L di by dt into potential across capacitor is q by c, so positive to negative again negative q by c, and again for this resistance I current is flowing positive to negative, so minus IR is the potential. So this should be equal to 0 as there is no battery source connected in the circuit. So we can take negative sign common and we can write it like this: L di by dt plus IR plus Q by C is equal to 0. And we can write I is equal to dq by dt, so it will be d by d square by dt square of q plus r times dq by dt, current is dq by dt, plus q by c is equal to 0. So now we can compare both these equation, and from that mass is analogous with the inductor, resistance is analogous with damping constant, and q by c is analogous to the spring constant. So we have L analogous to M, so L analogous to 1 by B, this is cancelled, N analogous to K cancelled, so L to M and R to B, and C analogous to, here it is mentioned to 1 by K and here it is mentioned to K, so here C is analogous to 1 by K, so option D will be the right answer. Let's move to the next one. A EMF of 20 volt is applied at time t is equal to 0 on a circuit containing series 10 millihenry inductor 5 ohm resistance. The ratio of the currents at t is equal to infinite to t is equal to 40 second is close to. So let's draw the diagram. So we have a 10 millihenry inductor in series with 5 ohm resistance, and we have applied at 20 volt. Here we have 10 millihenry or 10 raised to power minus 3 Henry. So we have to find out the ratio of currents, or in short we have to write charging equation for this, and charging equation for a LR circuit is given by I is equal to I node e raised to power bracket 1 minus e raised to power t tau. This is the charging equation. We have to find time at two conditions, current at two values of time, that t is equal to infinite and t is equal to 40. So first let for t is equal to infinite, I infinite will be I node 1 minus e raised to power minus infinite by 2, and as it is infinite, so if we divide infinite by some value, even infinite divided by infinite is again assumed to be infinite, so it will stay infinite. So I infinite is equal to I node 1 minus e raised to power minus infinite, and e raised to power minus infinite is e 1 by e infinite, and that is 1 by a very large value, so that will be approximately 0. So we can say I infinite is almost equal to I node. Now let's move to the 40-second time period, that t is equal to 40 second. For that t I40 will be I node 1 minus e raised to power minus 40 by tau. Now tau is equal to L by R. So L is 10 millihenry. So 10 into 10 raised to power minus 3 divided by R. So R will go here. It will come. So this will be 20 into 10 raised to power minus 3, or 2 into 10 raised to power minus 2. I think. Okay, let us write it. I40 will be I node 1 minus 1 minus e raised to power minus 20 into 10 raised to power plus 3. Okay, so this will be, and this will be e raised to power 20,000 in negative. So again, this will be I node 1 minus 1 by e raised to power 20,000. And this is a very large value. So again, this will be equal to I40 will be approximately equal to I node. And as we can see now, both of these currents are equal. And we have to find a ratio of I infinity by I40. Now by default, we know that in case of inductor, current increases an exponential curve. So I infinity will be slightly larger than I40, because to avoid the lengthy calculation, we just approximated, and their approximation comes out to be equal. But we don't have one as an option. But from the equation perspective, we know, and from the graphs, we also know that I infinity will be slightly larger than I40. So their ratio will be greater than 1, but that will be very small margin. And that is our option A, where ratio is 1.06. So 1.06 will be the right answer here. Let's move to the next one. In an AC circuit, instantaneous EMF and current are given by these two equations. In one cycle of AC, average power consumed by the circuit and the wattless current are. So we have to find the average power and wattless current. So first of all, let's find the power consumed. The power consumed in a cycle in an AC circuit, that is ERMS into IRMS into cos of phi, where cos phi is the power factor. Phi is here pi by 4. So ERMS will be, this is the peak value of the current, so 100 by root 2 into 20, that is RMS peak value of the current, 20 by root 2, and cos phi, any cos 45 means that is 1 by root 2, so 1 by root 2. Now root 2 multiply root 2, that will be 2, and they will cancel it on 10. So 1000 by root 2 watts is the power consumed in the circuit. Now regarding the wattless current, so wattless current is equal to I RMS times sine of the angle between current and voltage. So the IRMS is 20 by root 2, and sine 45 is again 1 by root 2, so 20 by 2, and that is 10 ampere. So option B will be the right answer here. Let's move to the next one. For an RLC circuit driven with voltage amplitude V mean and frequency omega node is equal to 1 by under root LC. This is angular frequency, so it is a resonance frequency, because we know resonance frequency is given by under root 2 pi, 1 by 2 pi into under root 1 by LC. And if you multiply omega and 2 pi and f, that is omega basically. So our circuit is at resonance, and it is also mentioned exhibit resonance, the quality factor of the circuit. So we know that quality factor of the circuit is XL by R, so that will be omega node L by R. Option A will be the right answer. Or we can also write it like, because at resonance we know XL is equal to XC, so that is also omega CR, 1 by omega, so CR. That can be also the value of quality factor. Let's move to the next one. A sinusoidal voltage of peak value 283 volt and angular frequency 320 per second. So here omega is 320 applied to LCR circuit. Given RLC, the total impedance and the phase difference between the voltage across the source and the current will be respectively. So we have to find out impedance and phase difference. So for that we need to calculate Z and XL and XC. So let's start with XL. XL is omega times L. Omega is here 320. So 320 multiplied by 25 millihenry, and this gives us 8 ohms. Similarly, XC will be 1 by omega C, 1 by 320 into capacitance 1000 microfarad. This will give us around 3.31 ohm. Now we can calculate Z. Z will be R square plus XC minus XL square. R is 5, so 25, and 8 minus 3.13, so that will be approximately again 5. We are approximating here, so 5 square, that will be 25, so root 50, or we can say 5 root 2 is the value of Z. From this, now we can calculate, we can say 5 root 2. Okay, or we have to calculate in terms of value because here we have 10 and 7. So root 2 is 1.41, multiply 5, that will be around 7. So impedance is 7 ohms. And coming to the phi, tangent phi will be XC minus XL divided by R, that is around negative 5 because XC is smaller, and R is 5, so that is minus 5 or minus 1, or in short we can say phi is 45 degree, and circuit is inductor dominated, means here current lags behind the potential. Or if we write the equation, suppose if V is given by V naught, that is 283 sine of 320 t. If this is the equation for potential, then for current, our peak, we can say that is 7, so current will be 283 divided by 7 times sine 320t minus pi by 4. This will be the equation for current. Let's move to the next one. An arc lamp requires direct current of 10 ampere at 80 volt to function. So from this we can calculate the power of the lamp, and if it is connected to 220 volts RMS 50 Hertz AC supply, the series inductor needed for this to work is close to. So as we know already that our arc lamp requires maximum current of 10 ampere. So in the circuit, suppose uh, we have a lamp here, this is our lamp, and we attach a say inductor with in series with it, and we have a 220 volt supply here. So maximum current in this circuit can be only up to 10 ampere, and if current exceeds 10 ampere, then this lamp will blow. So what will be the resistances available in the circuit? So inductor will provide its inductive resistance, and this arc lamp will also have its own resistance, and that resistance can be find out at as current through it is 10 ampere and potential across it should be 80 volt. So resistance V is equal to IR from the Ohm's law comes out to be R is equal to V by I is equal to 8 ohm. So 8 ohm is the resistance of this lamp, and for this inductor, resistance offered, the impedance offered will be omega times L. So total resistance or total impedance of the circuit will be R square, that will be 64, plus XL square. XL will be omega times L. Omega is 2 times frequency times L, that is we don't know. We have to calculate the value of L. So what we do here, we keep it as XL. We keep it as XL. So this is our first equation. Over from this we can say Z square is equal to 220, oh sorry, not 220, 64. Z square is equal to 64 plus XL square. Now we know that maximum current in the circuit is 10 ampere. So if I in the circuit is 10 ampere and potential applied in the circuit is 220 volts, from these values we can calculate Z. So Z will be, again, likely we calculated R for the length, then we calculate total resistance of the circuit, total impedance, that will be 220 by 10. So Z is 22 ohms. Now substituting this value here, so 22 square minus 64 is equal to XL square. And solving this, we get XL is equal to around 20.5 ohm. We have the value of XL, and now XL is equal to omega L. So omega L is 20.5, and from this L is equal to 20.5 by omega. Omega is 2 pi times the frequency, that is 50. So it is 20.5 divided by pi divided by 50 into 200, and solving this we will get 0.065 Henry. That is option B for us. So with this, I end this video here. Hopefully whatever I have covered till now is helpful to you. Again, if you have any doubts or suggestion, you can put them in comment section. I will try to solve them. And if you like this video, then do press like button, share it, and subscribe to our channel. Also, if you want to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.